The second example for variable slope method shows the solution of taking the volumes of base flow and runoff. You are in hydrology. How does variable slope method cut the base flow? Having a standard hydrograph, identify four important points. The first is the start of runoff, where the first extension is based. This extension ends at peak discharge. Now another extension happens from the end of runoff, and this extension ends until the point of inflection. After creating two more points of intersection, they are joined together with a third slope. The problem shows a storm over a catchment area of 50 square kilometers with an 8-hour duration. We are to determine the volumes of base flow and runoff using variable slope method, where we assume the inflection point of the hydrograph at t equal to 6 days. First is to draw every point of the hydrograph, taking time in days as the abscissa and the stream flow provided in cubic meters per day as ordinate. The hydrograph is a line chart with connected points. From the illustration, it is easy to eyeball the start of the runoff. The curve shows it as 165 at t equal to 2 days. The end of runoff, on the other hand, is computed from the function n as equal to 0.826 times the area raised to 0.2. Plugging in the area of 50 square kilometers, we get n as 1.81, which is rounded up to 2 days. This n is measured from the peak discharge, which tells that the end of runoff is at t equal to 7 days, because peak discharge is at t equal to 5 days. Now we can work on the variable slope. The first slope adopts the tangent from t1 to t2, and this is extended until it intersects the line of the peak discharge. The second slope uses the slope with the end of runoff. The slope at t7 to t8 is also extended, but only until the time of inflection point. The inflection point is located at t equal to 6 days, as stated in the premise. The endpoints are then connected to completely separate the base flow. To identify base flow per day, we use triangles. Now let's fill out the base flow table. Let's dive into the triangles we created first. The start of runoff has a triangle which covers T1 until T5, but provided heights are only 180 from T1 and 165 at T2. This is the start of the runoff. Using the readily available data, we can draw out a triangle with a span of 1 day. The height is then computed as the difference of 180 and 165, giving 15. The base flow at day 2 is 165, as it is the start of the runoff. Since we have the same slope all throughout the 4-day span, we can then solve for the location of point 3, as 165 less the daily change of 15, giving 150. Then that for day 4 is similar, taking 150 less the daily rise of 15, resulting to 135. And day 5 has 135 minus 15, giving 120 cubic meters per day. In case the procedure we just did is not that convincing, let's solve for the base flows using ratio and proportion. Just the same, we start with a triangle having complete elements. Then create a similar triangle covering day 3. This triangle also has 1 day span, and we are to compute for the height y3, using the same slope. By similar triangles, or ratio and proportion, we take the ratio of y is to x. From the model triangle, we get 15 is to 1 day. And this is equated with the ratio of the other triangle, which is y sub 3 is to 1 day. Cross multiply or just simply take the value, as there is the same denominator, taking y3 as 15 cubic meters per day. Use this height to solve for the coordinate, which is referred back to the level of 165. The point is below, so deduct y3. 165 minus 15 is 150. Do the same ratio and proportion procedure for day 4, where the triangle then has a span of 2 days, and we are to look for y4. With similar triangles, taking the ratio of y with x, the model triangle gives 15 is to 1, and the bigger triangle has y4 is to 2 days. By cross multiplication, you get y4 as 30, which is then subtracted from the reference level of 165. The base flow at day 4 is then 165 minus 30, giving 135 cubic meters per day. The computation for base flow at day 5 is still the same. The triangle this time is bigger, but has the same slope. The span is 3 days, and we are to solve for y5. By similar triangles, with y is to x ratio, we equate 15 is to 1 with y5 is to 3 days, yielding 45. The base flow for day 5 is referred from the level of 165. Then subtract the height of 45. The base flow at day 5 is then 120. So far, we completed the base flow under the triangle, but then we have left the base flow for T1 blank. To complete the table, take note that the start of runoff gave 165 as the base flow. Although T1 has more stream flow, we adapt the base flow as 165. This is the maximum volume of water infiltrating into the soil, not affected with the volume of the stream flow. Some computations do not include the runoff before the start, but technically it is still a part of the storm. After this, we can then continue solving for the base flow of the other triangle at the opposite end. To complete the base flow column, take the other triangle, which has a span of 2 days from T6 to T8. At T7, base flow is 210, and at T8 the base flow is 185. And we are still to determine the base flow at T6. To do that, identify the daily height. So taking the first triangle, y is then computed as the difference of 210 and 185, where y is 35. Solve for the base flow at day 6, adopting the same triangle, as the span is also 1 day. The base flow at day 6 is then 210 plus 35, which is 245 cubic meters per day. From the available base flows, T7 is 210 and T8 gives 185. Now let's move on to the direct runoff. This is the excess after water from the stream flow is infiltrated into the soil. At T1, the direct runoff is 180 less 165, which is 15, way too small to be illustrated in the small graph. At T2, direct runoff is 0 because this is the start of the runoff. At day 3, stream flow and base flow have a gap, which is actually the direct runoff. The gap is 195 minus 150, which is 45. DR4 is also taken as 245 minus 135, which is 110. At T5, the direct runoff is 360 less 120, which results to 240. Day 6 has 310 minus 245, which is 65. T7 is also the end of the runoff, so there is zero direct runoff, as illustrated in the graph. Then, as T8 has a lesser stream flow than the base flow of 210, all the volume of 185 will be taken as base flow. We have just completed the table. This time, compute for the volume of base flow. This is basically the area below the base flow separator, the computation of which is done by parts. Let's start off with the rectangle for span T1 and T2. The area is then 1 day multiplied by 165 cubic meters per day, which gives 165 cubic meters. The next area is a trapezoid from the span of T2 to T5. The second area is then the base of 3 days over 2 times the parallel bases of 165 plus 120, which then is 427.5 cubic meters. The third area is also a trapezoid, computed as 1 day upon 2 times 120 plus 245, which gives 182.5 cubic meters. The last area is again a trapezoid. The area then is 2 days over 2 times the quantity of 245 plus 185. This yields 430. Take the summation of all these areas, coming up with 1205 cubic meters for the base flow volume. Now for the volume of direct runoff, also computed as the area of the graph. The first area is from T1 to T2, which is a triangle. So the area is half of 15 cubic meters per day times 1 day, simplified as 7.5 cubic meters. 15 cubic meters per day is the DRH recorded in the table, or it is the height of the triangle. The second area is also a triangle, so it is computed as half of the height, which is 195 minus 150 multiplied by 1 day, giving 22.5 cubic meters. Now check on the next area, with the strips from T3 to T4, T4 to T5, then T5 with T6. They are all trapezoids. You can either solve for individual trapezoids per strip, or use the trapezoid rule learned from numerical solutions. This is basically just the collection of areas into a single equation. The third area then is the x interval over 2 multiplied by the different heights. The x interval in the graph is 1 day. The heights are the direct runoffs from the graph. So area 3 is then 1 over 2 times 45 plus twice of 110 plus twice of 240 plus 65. The third area is 405 cubic meters. The last area is a triangle computed as half of 65 cubic meters per day times 1 day, which is 32.5 cubic meters. The summation is the volume of direct runoff, which turns out to be 467.5 cubic meters.